Good morning, guys. How y'all doing? This is Mr. Robison. We're fixing to do the chapter 2 basic chemistry lecture. I know several of y'all have been asking questions about Mr. Robinson's boring rule of chemistry, and it will be answered in this lecture. I'm fixing to share the screen so we can go to the PowerPoints. Bear with me here. Okay, you should be seeing the PowerPoints now. Bear with me. You should see those. And he's hoping you're seeing these now. Okay, so basically in this chapter, one of the things I think that's very fascinating here is this is kind of a cool beginning of the chapter, and I'm not going to always go on these, but I'm convinced there's life somewhere else in our universe. And NASA, as you can see here in this PowerPoint, has a plans to go to Euphoria, one of the moons of Jupiter, where we now know there's standing water. It's like a slushy surface, okay, and we feel like there's probably life there. And also one of the moons of Saturn, Titan, has been found to find methane, ammonia, and hydrocarbons, the building blocks of life, as we will talk through this. So anyway, I'm very excited about that and about the possibilities of that. Here's an overview of the chapter very quickly: chemical elements, molecular and compound, molecules and compounds, chemistry of water, and acid base. We're just going to go through it kind of quick. A little bit of background physics here. Matter is anything that takes up space and occupies, has a mass and occupies space. Okay, and that's kind of cool. Can have up to what, 4 forms: solid, liquids, gas, and one you're probably not familiar with. I'm not, called plasma. Okay, but all matter, non-living and living, is composed of these basic 92 elements. Okay, and so an element is a substance that cannot be broken down into a smaller, to a smaller amount and still maintain the properties of that particular element. Okay, or another way to put it is there are 92 different atoms on Earth, or different types of atoms on Earth, or 92 elements that make everything on Earth. Or another way would be like there are 92 different Legos that make everything on Earth. Okay. Now, interesting enough, there are 6 Legos or elements or different atoms that make up 95% of living organisms, and these include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So you can see here the Earth's crust has a little bit more of silica and aluminum and iron and calcium, and in the red there is the living organisms. That's a pretty cool picture of a boardwalk, very similar to what we have here out at Sardis. Okay, so an atom then is the least amount of an element you can have to still maintain that property. So if you have an ounce of silver, it contains thousands of atoms of silver. Okay, now all of these 92 different elements that naturally occur on Earth. Now we will see in a minute in the periodic table that there are other ones, but those are man-made in a laboratory. Okay, so everything in the universe is composed of these different 92 naturally occurring elements. Okay, and so the least amount of that element you can have is an atom. Now they all have the same basic subatomic structure. All atoms are made out of protons, neutrons, and electrons. Okay, and as you probably already know, the protons and neutrons exist in the nucleus that I'm pointing to with a little pointer, and the electrons circle the nucleus, right? And they have never been seen. And we have seen protons and neutrons with electron microscopes, got down to that level, but we have never seen an atom. Okay, which is pretty fast. I mean, it's never seen an electron, but we know they're there, just like no one has ever seen a bullet coming out of the car, but you've seen the bullet's effect on other things. So physicists have proven that they're there. Protons have been given a weight of 1 subatomic unit. They have a charge of +1, so they have a charge on them, and they reside in the nucleus. Neutrons have no charge, that's the name neutron, neutral, and a weight of 1. Electrons are -1 charge and have a weight that is extremely small, like 1/1400th of an atomic unit. So you'd need like 700 electrons to round up to 1. So when we do chemical formulas, we don't really talk a lot about them. They're not that big as far as weight of a substance, okay, or a compound or molecule. Okay, and you can see here, so the protons, neutrons in the middle, and then the electrons circle in these orbitals or bands. Okay, now, as in Robin's belt, as fatter I get, the bigger my belt. As we go farther out to different shells, the shells get bigger and they can hold more electrons. And that's a big thing about subatomic chemistry. Okay, you can see here, we're just kind of showing some more of these, just kind of walking through those. Now, when you look at a periodic table, you will see a number at the top, and that is the mass number. And the number at the bottom here is called the atomic number. So the atoms are in order of weight, with number 1 being the lightest atom on Earth, and 92 being the heaviest naturally occurring atom. Okay, it has the largest mass number. The atomic number tells you the number, its atomic number, the number of protons it has, and the number of electrons it had at creation of the universe, or at the Big Bang, or when God did it. And I think all of them are one and the same. The symbol is a letter, represents that atom, and the mass number is the number of protons plus neutrons in that atom. Carbon, as you know, is carbon number 6, and it has the most common weight is atomic weight of 12. Okay, so backing up there, the atomic number equals the number of protons. The mass number is protons plus neutrons, and the atomic mass is approximately equal to the mass number. Okay, atomic mass. Okay, now that's not okay. The atomic mass is approximately equal to the mass number. Okay, now moving on. Okay, so here's our periodic table, and you can see that this is the top part of it. That we have these periods that go up and down, and groups that go across the right. Another way to think about this is that this first group is the first electron shell. The second line here, our group, is the second electron shell, third shell, fourth shell. So as we go down the line, we are going out. And as we'll find out, is the first shell can hold 2 electrons, but the rest of them can hold, like if they get to 8, then they're cool, and then they skip down to the next shell. Even though some of these other shells can hold more, we'll do it as an equation, 2x squared, that tells you the number of electrons that shell can hold. So if you put 1 as x, x squared is 1, 2 times 1 is 2. And if you take 2 squared is 4, 2 times 4 is 8. So the second shell can hold 8. The third can hold 18, but it holds 8 and flips over. It then sends the next electron to the next shell. Now, I'm not going to get into, I'm not a chemist, but I can tell you that that's just the way God made it. That's one of those rules of Earth. It's actually called the rule of octave. We'll talk about later on that all atoms want to do is to be stable, okay? And they will either share or steal electrons in order to get stable, okay? And we'll talk more about that. But you can see also the number at the bottom here, the atomic weight, is not equal. That should be 1. So what does that mean if it's 1.008? That means there's some hydrogens out there that have an extra neutron in them that makes the average of all the hydrogen in the universe weigh 1.008. And those are called isotopes, and we'll talk about those more in a minute. And you'll notice that most of the things that make up life, carbon, hydrogen, and oxygen, are at the top of this shell of the periodic table. Once you get below 36, you get into some rare earth elements that we don't really have a whole lot in our body. And so I'll say that for the chemistry department when you're taking chemistry, but for me, we're worried about the top here where life exists for us. And there's some good notes here about a little bit more about the groups and stuff. An isotope, as I said earlier, is an atom that has extra neutrons in it, and therefore has a different atomic mass. Now, the most common carbon is carbon 12, and notice that all of them have the same number of protons and electrons, but it is the addition of neutrons that give it the more famous one you may have heard of is carbon 14. It's used to do radio dating things, and it's pretty accurate within 500 or 600 years, maybe 1,000 years of radio dating how old something is, or when was it alive. Okay, so carbon 14 is 1. Now, so all of them together give you that number that we saw back in the periodic table here for carbon is 12.01. Now, the question that some of y'all have been asking me about Mr. Robison's Barney rule of chemistry, we're going to get into that. And here, I'm going to go ahead and throw it at you here. And here's the deal. What determines how reactive an atom is how many electrons it has in its outside shell. Now, my oldest daughter was a huge disciple of Barney, the purple dinosaur, so that's why I called it Mr. Barney's rule of chemistry. And I steal it from Mr. Barney because he wants everybody to be what? Come on. I love you, you love we. We're there you go, happy family. So everybody wants to be happy. And so I'm going to define happy in chemistry, and therefore you're going to learn chemistry by my stupid Mr. Robinson's Barney rule of chemistry. So in order to be happy, an electron needs to have a full outside shell of electrons, then it's happy. And then if it can steal them, it will. If it can share them, it will. Okay, let's think about that for a second. So if that's true, then hydrogen has one atomic number 1 has 1 proton and 1 electron at the Big Bang. How many electrons can the first shell set? I just said it can hold 2, so hydrogen is not happy. It binds to everything, and everything you buy at Walmart to eat has hydrogen in it. Hydrogen is probably the most common atom out there. It's stuck to everything because it ain't happy. It will grab another molecule, another atom, and share an electron with it. It'll share its 1 electron with one of the electrons of another atom or molecule, and therefore be semi-happy. Not super happy, but happy enough. Helium, atomic number 2, has the second shell full, and it is an inert gas. The only thing you can do with it is electrocute it, and it glows for neon lights. For helium, excuse me, put it in a balloon. That's neon light. Sorry, that's the second inactive gas or happy atom. Helium floats a balloon. That's it. It's nothing you can buy. There's nothing you can buy at Walmart to eat that has helium in it. Helium floats. Helium makes great, Goodyear blimp over a sporting event, and it will not blow up or burn. You may remember the Hindenburg the Germans had in the early part of the last century. They used hydrogen in it, and it's not super happy, and so it did blow up. So a hydrogen tank can be quite explosive. Helium will not blow up. Neither will neon do anything. Here's another one I've worked with. Argon, atomic number 18, has a third shell with 8, and it's very stable. It is used to clean things. It is used to clean silicon boards where they make the computer chips that go into our phones and our computers. In the movie Terminator, when they blow up the building, that's the gas that seals the room. They shoot argon in to force oxygen out of a room so it can be used to put a fire out. Because if you fill a room with argon, there can be no fire because argon will not burn. So getting rid of the oxygen is one way to stop a fire. So anyway, kind of crazy. Everybody on this line is inactive and will not bind to anything, including my favorite 36, kryptonite, that we all know makes Superman unable to have his superpowers, which we'll save that for another lecture over in Supernatural chapter and part 2 of Major Biology. All right, anyway, so isotopes then all have the same reactivity because they have 6 electrons, but they have a different atomic weight. And this also makes them very unstable because they will spew out subatomic particles, and that spewing out of subatomic particles is what we call radiation. So radiation is the release of energy from a subatomic particle in the nucleus. These neutrons, they decay and they spew out. Now, we use that for x-rays. We use that, here we are, for an MRI to see this woman has thyroid issues. Low doses can be used for CAT scans. We also can use it, pinpoint radiation, to kill this brain tumor. You see that brain cell tumor dying. So it's used for treatments, right? And of course, x-rays is probably one of the more common things. Now, the danger is if we have a radiation spill in our environment, then this carbon-14, for example, would be taken up by plants, and it would be just the plants, and you and I can't tell the difference between the radioactive carbon-14 and regular carbon-12 because it has the same number of electrons, so its reactivity is the same. So Mr. Robison's rule of chemistry is all atoms want to do is be happy, and to be happy, they have to have a full outside shell of electrons, okay? And so these only happy atoms really are helium on the far right, on the period right, the period group on the far right there, group 8, and those are our inert gases, okay? And as we look at molecules, everybody gets happy, and that's what holds water together, that's what holds sugar molecules together, and so that's a huge concept. It's also called the rule of octave, rule of 8. So if you get 8 electrons in the outside shell, it's stable. I once described that as like, if you ever had a tire that had a wobble in it, and maybe you're missing one of the little lug nuts. Well, imagine a perfectly balanced tire. That is 8 electrons in the outside shell, or 2 in the first. Okay? Now, here's a really cool one here that I have trouble understanding. So look at this. This is a good PowerPoint slide here. Electrons are attracted to the positive charge of the nucleus because of the protons, and it takes energy to push them away from that shell. So the farther they are away, the outer shell they're in, the more energy it takes to keep them out there. So what we're going to see a lot of times in photosynthesis is we fire up electrons by carrying the electron to the outside shell, and that energy is released to build sugar later on when we talk about mitochondria making ATP and the photosynthesis making sugar, making ATP to make sugar. So that, to me, that's a very important here. So electrons determine the chemical behavior of an atom. That's a good PowerPoint there. Bohr's model is talking about the electrons, right? And that first shell can hold 2, the second shell can hold 8. And if we can get a full outside shell, meaning 2 or 8, 2 in the first shell or 8 in any sequential shell out, then everybody's happy. Okay, this outermost energy shell of an atom is called the valence shell. That is the one that's going to determine the reactivity. The rule of 8, if they can get 8 out there, then it's the most stable. Okay, and it goes on. I think I beat that horse in the ground. Here's a couple here. Hydrogen, right? 1 ain't happy. Carbon, 4 electrons, and we'll talk about this in the next chapter, is the building block of life because it can form 4 bonds with other atoms. Oxygen has 6 in the outside shell, so it needs to bind to 2. So 1 oxygen needing 2 electrons can bind to 2 hydrogens to make one of the most common compounds on Earth called water. Okay, water is real common. And here are the models of these atoms, and you can see some of the sulfur and phosphorus, etc. Okay, so molecule is any 2 different elements bound together. A compound is two different elements Okay, but a molecule could be two or more elements bound together. Okay, and a formula tells us the exact number of atoms in a molecule. For example, glucose is C6H12O6. You can see compounds there, carbon dioxide, water. If it's the same thing, it could be a molecule, right? So H2 is a molecule of hydrogen. You don't find any H in nature. You don't find any O in nature. And what it's done, it's already sharing electrons. So hydrogen, H2, is sharing two hydrogens sharing their one electron, and it ain't super stable, but it's stable as it can get. Okay, there we go. Compounds, molecules, kind of cool. Moving on. Okay, now our next big short answer question are the three types of bonds, right? We've already been talking about them. Okay, all right. So there are three types of bonds in nature. There are ionic bonds, where we're going to steal electrons, and these atoms, once they lose electrons, they become positive charge, and if you gain an electron, you become negative charge. And that attraction of opposites attracting is the ionic bond. Covalent bonds are when you share electrons. I also call that the Barney bond because they like to share electrons. And then the hydrogen bond is the weakest of the three, and it is a weak attraction between hydrogen in a polar covalent bond and another atom also in a polar covalent bond, usually oxygen, but it can be nitrogen and some other atoms. Okay, so we'll do ionic first. Any atom that has gained or lost an electron is said to be an ion. Okay, and that attraction between the negative and positively charged ions is called the ionic bond. Now, the most famous and easiest one, and y'all have ever been out in the woods, you've seen salt licks, natural salt. Sodium, when the Big Bang occurred, has an atomic situation where it has one electron in its third shell because of its weight. And if you go back and look at sodium, let's go back. Sodium has atomic number 7, and chlorine is atomic number 17. So let's look at 7. So 7 is going to have, I have to back up and check, 2 electrons in the first shell, 6 in the second shell, for 8, right? And I get that right? So, excuse me, it has 2 electrons. Let's do that again. So atomic number 7 would have 2 and 5 in that second shell, right? I think that may be wrong, right? I do that right? Chlorine, we said, has 17. So 2 and 8 is 10. And then in the outer shell, it has 1, 2, 3, 4, 5, 6, 7. Okay? So 2, I think that may be drawn wrong. Okay, so sodium, let me back up. Maybe I read that wrong. I did nitrogen is 7. Sodium is, I'm losing my mind. Sodium is 11. I'm sorry, I read that wrong. I was looking at nitrogen is 7. So sodium is 11, sorry. Forgot my basic chemistry. So 2 in the first shell, 8 in the second shell. That's 10 and 11. 1 is the loneliest number. 1 electron in that outside shell. So is sodium happy? No, it needs to get rid of that 1 electron. Is chlorine happy? No, it has 7 electrons in its outside shell, so it needs to grab an electron. So when God created the universe Big Bang, all the sodium laying next to each other said, hey, dude, why don't you take my electron, and then I will be happy? And when it does, sodium becomes a what? If you have a negative, lose a negative, you become positive. So it's a +1 ion. So an ion is nothing but an atom that has gained or lost an electron. Chlorine now has gained an electron. It is now stable with 8, but it is a -1 charge. So when that sodium ion electron leaves and goes over, you create a sodium that has a +1 charge and a chlorine with a -1 charge. Opposites attract. That's our ionic bond, and bam, you got table salt. There it is. Isn't that the coolest thing ever? So sodium with not 7, that was nitrogen, but 11 is unstable because it has 1 electron in its outside shell. So when God created the universe, all the sodium and chlorine laying next to each other, the chlorine stole an electron. It became a negatively charged chlorine ion, and sodium became a positive charged ion, and they attract, and that's a big old pile of salt there. And when salt is put in pure water, they will pull apart and go in solution because water has a little charge on it too, as we'll see in a minute. That's pretty freaking fascinating to me. Okay, so that's our first type of bond, ionic bond. Covalent is a little bit easier to understand, and that's where electrons are shared. Okay, so here is hydrogen gas, H2, and they are sharing their 1 electron with each other like so. Now, it's not as stable. It's very explosive. You can blow a room up with a tank of that. Oxygen's a little more stable because it has atomic number 8, so it has 6 atomic number. Well, I should know my atomic number. I believe oxygen is, what we got here, 2, 8, and so it's got 6 in the outside shell. As 8, atomic number 8. Not happy. And so it has to share two sets of electrons. So when we have that one stick there, it's a line or stick, that means they share an electron. Two means they share two electrons each. So oxygen has two of its 6 electrons in the outside shell, shared with another oxygen with 2 of its 6 electrons in its outside shell, and then they all circle each other, and we have a state of stability. Not as stable as other things. Obviously, hydrogen is much more volatile. It will blow up. If you ever seen an oxygen tank blow up, it burns like an acetylene torch. So this is why we're very careful in the hospital with mothers around oxygen. I'll show you nitrogen in a minute, and that is my number 7. Sorry. So it has 5 electrons, and that second shell needs 8. So they share 3 electrons for a total of 6. So nitrogen gas that makes up 80% of our atmosphere is very safe because it's not going to release energy because it has 3 covalent bonds, sharing bonds. And these are equally sharing bonds too. So these are said to be nonpolar, meaning they're equal sharing. Here's methane with carbon with 4 electrons, 4 hydrogens stuck to it, sharing 4 electrons. Okay, pretty cool. Okay, so now what it talks about polar and nonpolar. Polar covalent bonds share electrons unequally. Okay, and so water is a great example of this. Water, when drawn, is like this, and this angle, instead of being 180, it is, I believe, 108 degrees right here. So it gets a kink in it because oxygen has 8 protons, hydrogen has 1 and 1 proton. So these 1 electrons that they're sharing are going to be over here more because of the 6 protons than over here. And that creates a bend in it, and it also creates a slight charge over in this area, a slightly negative charge over here, and a slightly positive charge on this end of the water molecule. And that leads to what we call a polar, meaning charged, unequal covalent bond. Okay, and that leads to the hydrogen bond, which is this weak attraction between a slightly positive hydrogen atom and a slightly negative atom that could also be the oxygen on water, or it could be another compound. So this is what water looks like. Water, oh, it's 104.5. I was close. I said 108. So the angle is 104.5, and this makes this area negative and this positive, and then that weak attraction between hydrogen in a polar covalent bond and another atom, in this case oxygen, forms the hydrogen bond. This is why water sticks together. This is why boats float. This is why you can swim. And this is why ice floats. This is super cool stuff here, and that is the hydrogen bond, the weakest of the 3 bonds. So we had ionic, where you have charged atoms, negative and positive attract, sharing, covalent, and then this hydrogen bond, which is what holds water together. Because it's so cool, there's a couple of weird things that makes water have. Water has a high heat capacity, means it can store heat. This is the amount of energy it takes to take ice into liquid. There is 80, and then another 540 calories to make it vaporize. When you boil water, you break in hydrogen bonds and create water molecules that go up into space. And there is, I'm going to send that to voicemail, and I'll call her back here in a minute. Sorry about that. I was trying to take one this morning before class. Water has a high heat evaporation. We just saw that, and it's an excellent solvent. Okay, so we sweat and water evaporates, and that cools us. It is the main solvent of all molecules on Earth. Water has a hydrophobic end that hates water, and a hydrophilic end that likes water, and we'll look at that in the molecular structure of water. Okay, any ion can go in solution. So Gatorade is basically water with elements that you sweat out, put back into it, and those are the ions that you need. Like we don't need a lot of sodium, but chlorine, potassium, other ones are needed, right? And so it's basically replacing some electrolytes that we urinate out and sweat out. So it's the universal solvent on Earth. It holds together each other by hydrogen bonding, and that's why plants are able to carry water to the top of the tree by evaporating water at the leaf. And we create a pool up very similar to how straw works, right? When you suck on the straw, the water can go through. And if you've ever used a water hose and stolen gas from somebody, then you know, or maybe you had to take it out of your car to put it in the gas. Should say stealing. Maybe you let someone borrow some gas, and that is the hydrogen bond is what allows that to happen. Another cool thing about water is water is less dense than water. Gets maximum as it gets colder. As it goes from, let's say, 25 degrees centigrade down to about 4 degrees, it reaches maximum tension. So it can't get no tighter, then it starts to expand. And so water expands as it reaches below 4 degrees, and therefore ice floats. So the molecules are farther apart in the ice than they are in the 4-degree water. So ice always floats, and 4-degree water goes to the bottom of the lake, and this prevents a lake from freezing from the bottom up. If it weren't for hydrogen bonding, all the fish would be on top of a frozen lake, and it would be a one-time event. There'd be no life in that lake because it would freeze from the bottom up. It'd be like fish laying at Kroger's. But because at 4-degree water always is the heaviest, it stays the bottom, and the bottom of the lake will be the last thing to freeze. And it's possible to freeze the whole lake, but it rarely ever happens, right? Ice can also act as an insulator, and so that's why that ice on top keeps the water cooler below, warmer below it. The igloo is a good example. It can be used as an insulator. Here are that ice floating with these seals on it. That's pretty cool, right? Here's liquid water. Look how tight it's packed at 4 degrees, and here's ice. The latex is bigger, and this is why if you've ever filled up, put a beverage, a Coke or Dr. Pepper or whatever in the freezer to get it cold real quick and forget about it, it blows the container up, because as it reaches below 4 degrees, it will expand and blow up in that freezer. And that brings us to acids and bases, okay? And this is a cool little thing here. pH is a term that drove me crazy for years until I was in grad school, and this gentleman explained it to me. Didn't always like how he did science, but he sure did teach this one to me. But pH is a measure of the hydrogen ion concentration in a solution. The actual equation is pH is the negative log of the hydrogen ion concentration. Our pH equals negative log of the amount of hydrogen ions per gram per liter. Okay? Now, for a long time, you've probably heard of acids are things that release hydrogen, bases are things that grab hydrogens up. But that pH scale going from 1 to 14 always drove me crazy. I think that was stupid. 7 is neutral, and I wondered why. And that drove me nuts, because I think it should be 10 is neutral and 20 is the top of the scale. Well, there's method to the madness. And the truth is, the pH scale is based on the physical properties of water. So if you get pure water and measure its gram per liters and put it in a calculator, take the log of that, you get -7. So 0.0000007 decimal places, grams per liter of pure water dissipate into hydrogen ions and hydroxyl ions, and that is neutral water. Okay, and as you go to pH of 1, then it has a way more hydrogen ions in it than pH of 14. So every number on the pH scale is like the earthquake scale. It's a factor of 10. Okay, because of the log function key. So pH 4 is 10 times more acidic as pH 5, and then 4 to 6 would be what? 100 times. The pH is 100 times greater than pH of 8. So as you go to 10 to 8 is 100 times. So every point on pH is times 10. Here's some common things. Water being neutral, but milk is on the acid side. Look over here. Stomach acids, lemon juice, all these sodas are very strong acids. Matter of fact, I always tell this one: if you take a Coke and pour it over your windshield, when you got a bunch of bugs stuck on it and your windshield juice is out, it'll burn the bugs off the windshield. It's an acid bath. And on the other end, sodium hydroxide, oven cleaner, very dangerous in your household. Ammonia, that was very dangerous to children or anybody eating this. And these are strong bases that can be used to clean things. Blood's a little bit on the base side there, 7.2 or so. But anyway, it's pretty interesting chemistry here of that. And we'll talk more about that in class. So pH is a negative log of the hydrogen ion concentration. And it is based on the natural physical properties of water. Okay, and that's very important. Buffers are anything that prevent changes in pH. Okay, and so they will prevent shifts in pH. They can release hydrogen or grab them based on what is needed. And probably the most famous one is bicarbonate. HCO3 can grab a hydrogen or it can release a hydrogen. So Rolaids is buffers. Okay, and I believe that is pretty much on that, but I wanted to get that Mr. Barney rule of chemistry that a lot of people were asking about, and that is kind of an overview of chapter 1. All right, I'll see y'all in class on Tuesday and Thursday. Have a good day. Bye.